to take those little representative rectangles today, and we're going to start spinning those representative rectangles to make some fun little shapes. What's that? It's a blast. All right. So you should be able to find the volume of a solid. So when you spin a function around one of the axes, either the x-axis or the y-axis, or maybe even just some random line, it's going to generate a solid. Our goal is going to be to find the volume of that solid, and we have two methods to use for that. One is called the disk method. The other is called the washer method. So it's fun times 2. And then get a pen that works. There you go. You should give at least 2 hugs today. Has anybody already done their 2 hugs today? You got your 2 in? Good. Excellent. Doesn't mean you have to stop at 2.
It says at least.
At least, right. Yeah. And this is a math classroom, so we should know that that's x is greater than or equal to 2. Good. All right, the disk method. Here we go. So remember those little skinny rectangles I was drawing? That's one of them. I just blew it up. Okay. So I made it wider, and it looks like that. Okay. You with me so far? Yeah. Good. Then I'm going to take this and I'm going to spin it around this thing called the axis of revolution. The thing to notice is that this rectangle is on the axis of revolution. In other words, it's touching the axis of revolution. When I spin that rectangle around, it generates this thing called the disk. Hence the reason we're using a disk method. Okay, so let me give you a second to digest that before we move on and start generating formulas and stuff like that. R in that picture is the same thing as the height of our rectangles from the problems in 7.1. W is the width. You could also use delta x. You could also eventually, we could use dx because we want it to get really tiny, but we'll get to that in a second. Okay, first big question. What's the volume of that disk? I told you there's some geometry there. How do you, first of all, what shape would you know that as from geometry? It's a cylinder. How do you find the volume of that cylinder? Mason? Pi r squared times h. Good. And with respect to this problem, what's r?
R.
Good. And what's h?
W.
W. Everybody good? So it's a cylinder on its side. That leads us to that. Pi r squared is the area of one of the surfaces, and you multiply it by the thickness to give you the volume of the cylinder.
Can you go back?
Area of the disk times the width of the disk. And you know that's important because it's in an orange rectangle. Here's how we're going to generate our solids. If I take one of those disks, one of those rectangles, and I spin it, I get that yellow thing. If I then look at the next rectangle over, and the next rectangle over, and the next rectangle over, going left and right, eventually I'll end up with that 3-dimensional solid. So here's the 2-dimensional stuff we did yesterday. Spin all of that, and we end up with that 3-dimensional solid. It's not a very pretty 3-dimensional solid. How can we make it prettier?
Make it a cone.
I'm sorry?
You can make it a cone by smoothing out the sides.
We could make it a
Smaller
cone.
rectangles.
I'm sorry?
Smaller rectangles.
What will that do to the picture?
Make it smooth.
Make it smoother. Good. How small do we want those? How skinny do we want those rectangles?
Super skinny.
Super skinny. Correct. So again, here's the ugliness. You take a big fat rectangle, you spin it, and you get these things. We want it to look like the blue thing, nice and smooth. And so if we do that, we can take W or delta x and shrink it down really skinny into dx. Okay. Again, 2 techniques. Skinny rectangles or more rectangles. We like the skinny rectangles. So now we have a cool little demo here. Okay, so here's my function. I chose to use 2 times the square root of x, and my axis of revolution is over here. I don't want my axis of revolution over here. I want my axis of revolution, I'm in the wrong thing. I'm going to put it there. No, I'm not going to put it there. I'm going to put it over here. Now, here's the first challenge. There's my axis of revolution. This one happens to be vertical, it doesn't matter. What I want you to try and visualize is what is that solid going to look like when I spin it around that axis of revolution. Okay, so a little thought experiment there. Try to picture what that's going to look like. Will it have a hole in it? Will it be a solid figure? Does it go to a skinny point? Is it wide all the way around? Et cetera, et cetera. So you can see as it spins, you get that weird looking thing. So it's almost like a cylinder with a cone taken out of it. Okay. Let's go back to something a little bit simpler here. Okay, I'm going to reset. Different function, just the square root of x. There's my representative rectangle. It's fairly wide. When I spin that representative rectangle, I get that disk that we talked about. Okay, can you see that there? Now, if I continue to move left and right and add more and more rectangles, we get something that looks like that. And as we said, if you shrink the width of that rectangle, it will smooth out that shape, and that's really what we want. We want it to be as smooth as possible. And we can move the axis of revolution. We can revolve it horizontally. We can revolve it vertically. Have a great weekend.
You too.
Okay. Our eventual goal is going to be to find the volume of that thing. So how do I do that? We've established that we can find the volume of one disk. How do I find the volume of the whole shape?
Integral.
Integral. Good. Come on. There we go. Okay, so we'll use this as an example. Took my function x squared plus 3, and we bounded it, or I bounded it by 2 vertical lines, -2 and 2. So we're going to revolve that yellow region. In that yellow region is my blue representative rectangle. And notice that this is the first time that I reduced delta x to dx because we want that to be really skinny. When I spin that, I'll end up with that funky thing on the right. And, yeah, it kind of could look like a yo-yo. So first things first, I'm going to find the area of the rectangle, just like we did yesterday. Top minus bottom gives me the height of that rectangle. Dx is the width of that rectangle. What's the radius of the disk? Yeah.
You said top minus bottom, what do you subtract?
Let me see if somebody else can answer that. I said top minus bottom. What am I subtracting?
Like the function from the top minus the function on the bottom and take the integral.
But he just asked, what am I subtracting, Eric?
Once again, the line that you're revolving around, right?
Axis of revolution. In this case is what? 0. Right. Yeah. That's why you're wondering where the minus is, right?
Yeah.
Yeah, because it's minus 0, because I'm doing it along the x-axis. So the volume of that disk, this is the radius of the disk. The height of the rectangle is the same as the radius of the disk. The width of that disk is dx because we want it to be really skinny. So we plug into that formula pi r squared w. Or pi r squared dx. How many of those disks do I want? An infinite. Going from where to where? -2 to 2.
Wait, so R is the area of the
R is the radius of the disk, which is the same thing as the height of the rectangle.
Can you repeat that?
The R is the radius of the disk, which is the same thing as the height of the rectangle.
Okay.
Yes or no?
Yes.
Okay. So here's my rectangle,
Oh, and then R is just
and then when I
Y.
spin that,
What?
I generate the disk, and the radius of the disk is the same as the height of the rectangle. Okay. The thing to notice here is that, and this will come up later, the representative rectangle is always touching the axis of revolution. Because what we're going to look at next is what happens when it's not. I FN into that, but how would I do that integral without a calculator? Yeah, not the chain rule. There's no chain rule in integrals. Distribute? U to U? Okay, would U to U work? What's U? X squared plus 3? Is it going to cancel with anything? No. It's not distribute, but
Like just multiply it.
yeah, multiply it out, FOIL. What is x squared plus 3 squared? Good. Plus 6x squared plus 9. Good. Why did I move the pi out in front? It's a constant, right. So why get it involved with all the other antiderivative stuff when I can just slap it out in front and not worry about it till the end? In a problem like this is a reasonable integral to expect you to do without a calculator. This is not a u to u, you have to multiply that puppy out using the rules for foiling that. It's not x to the 4th plus 9. Don't make that mistake. Okay, so before we move on, are you okay with this whole system? Yes or no? Any confusions? All right, so the trick here is understanding the geometry, that we're starting with this rectangle, and as we spin that rectangle, we get a disk. Here's how you find the volume of the disk, and then integrate to add up all those disks. Dan?
So is the dx just the w then?
Yeah. We started with a big fat rectangle, and I want w to be really, really tiny to make the curve as smooth as possible.
Will it always be dx?
Yeah. No, because it could be dy. But it'll be a differential, whether it's dx or dy, depending on whether we revolve it this way or we revolve it that way. Okay? We good? Yeah. Good. All right. What if we spin it the other way? So here's the one we just did, where my rectangle is touching the x-axis, or the horizontal axis of revolution. We spin it that way. Everything's in terms of x. Our differential is dx. We revolve it around that horizontal axis of revolution. If you spin it along a vertical axis of revolution, radius is still the same, but just like what we did yesterday, everything now has to be in terms of y. Your function is in terms of y. Your differential is dy because it's the change in the thickness vertically. The process is exactly the same though. Common mistake here is people miss that squared. Remember, it's pi r squared dx. Pi r squared dy. Pi r squared dx is the volume of one of those disks. What, too fast?
Yeah.
Okay.
Does it matter which way they spin around the x-axis?
No, and in fact, we'll do some problems where you'll look at a function and you'll do, similar to what we did in 7.1, you'll look at it, spinning it one way and then spinning it the other way. And you get completely different shapes.
So then it does matter.
Okay, you got me. It matters as far as the answer and the shape goes. It doesn't matter as far as the method goes. The attack is the exact same way. Okay, so case in point, if we look at the example we did yesterday with the, let's suppose we take this triangle that we talked about yesterday. If I spin that triangle around the y-axis, what shape, what did I get? What volume or what shape will I get?
Oh.
Cone. Any problems with that? Okay, what if I revolve it around the x-axis? What do I end up with?
An inverse cone.
An inverse cone. Yeah, it's a cylinder with a cone ripped out of it. And for the most part, you're not going to be expected to draw these three-dimensional figures. Okay. So if I spin it around the y-axis, you'd get a cone. If I spin it around the x-axis, I'd get something that looks like that should be dashed. Something like that. Okay, where again, it's a cylinder minus a cone. Basically.
Wouldn't they have the same area?
Same area?
Yeah. I mean volume. Sorry.
No, they would not, because the one that's spun horizontally would be the volume of that cylinder minus the volume of the cone that you get from spinning it the other way.
Yeah.
Okay. All right. Then I had an example for you. This one we want to do around the y-axis, so we're going to change things up a little bit and just look at it. I don't know if I have a picture. I don't have a picture. Do I have a picture? No picture. Okay, whoa, easy. I just turned up the volume. Okay. So let's do a sketch just so we can see what's going on here. Or we could just do that. Strike one. What? Third time's a charm. Yeah! Do you have any idea what x to the fifth looks like?
Yeah.
No clue?
It's got 4 changes in dimension. I got vertices. 4. What's it called?
I don't know.
Oh, I know what you're talking about.
Skinny
So what's
version
vertical
of
x?
X. Take a steeper X cube.
Does it look like this? Is that what you're trying to say?
No, it's got 4 points of dimension.
It's got 4 vertices. So 4. Duh, 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 duh. It's like,
Duh, 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 duh.
yeah, like
No, it
that.
doesn't. No, it's like X cubed.
That's what he was going at, but
How about we get out a calculator? Somebody graph x to the fifth and see what it looks like.
Oh, never mind.
It doesn't go like da 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 da. I know that much.
It goes like,
This goes like this.
it goes, yeah.
Yeah, it's pretty much x cubed. It just
Skinny. That was if it had
kind of looks like a tangent graph.
plus X and 4.
All right.
No, it's skinny.
So once we get an idea of what that looks like, that took a while. We want to bound then the graph between this function, y equals 1, and y equals 32. What's the line y equals 1 look like?
Horizontal.
Horizontal line through 1. And a horizontal line through 32. And so we're talking about that region. Okay? And we're going to spin that around the y-axis. Okay, so notice what I'm doing in my picture. Not only am I finding the region, the bounded region that I want to find the volume of after revolution, but I'm also denoting where my axis of revolution is by using the little arrow. Next thing, I need a representative rectangle. Will that representative rectangle be horizontal or vertical? It's horizontal. Okay. What's R?
X to the fifth. X to the fifth.
Just as a clarification, that's x to the fifth minus 0. Right minus left. But since left is 0, we just get that. How thick is that rectangle?
Yes.
No.
dy.
dy. Okay, now do we see a problem here? What's the problem?
You have X to the 5th equal. You're trying to take the perspective line.
Yeah, we're using dy, but the function is in terms of x. How do I solve that problem?
x to the 5th equals y.
Uh-huh.
So we can substitute.
Take the fifth.
So R equals
Yeah,
Y?
so instead of x to the fifth, we're going to do the fifth root of y.
Oh, exactly.
You're such a coward.
Wait,
Yes?
you can't just say R equals Y.
But r doesn't equal y. R equals the fifth root of y. Because I'm working horizontally, everything has to be in terms of y. So what I did is I took this and I solved it for x.
If r equals x to the fifth and y equals x to the fifth, doesn't r equal y?
No. R equals x to the fifth, and r also equals the fifth root of y. I just came over here and I took the fifth root of this side and the fifth root of that side.
Oh, because you need r in terms of that.
There you go. Okay, so far? Spin that. If I spin that, I get something that looks like this. There's my little disc. What's the volume of that disc? Just go ahead and shout out the answer.
I.
Pi, good start. Pi.
R. X to the fifth.
No.
Five.
Fifth root of y
Squared.
squared dy.
As integral.
That's the area. Sorry, that's the volume of one disc. How many discs do I have?
Infinite.
A lot. And I'm taking discs from where to where? We good? You can move the pi out in front so it stays out of the way. What's x to the, what's the fifth root of y squared? Y to the 2/5 or y to the 5 halves? Y to the 2/5. So this is the same thing as pi times the integral from 1 to 32 of y to the 2/5 dy. What's the antiderivative of y to the 2/5?
5/7 y to the 7.
Good. 5/7 y to the 7/5. Evaluate it from 1 to 32, and then take that whole thing and multiply it by pi. Can we stop there, or do we need to keep going? Let's keep going. Okay, what happens if I put 32 in for y?
You did a big number.
You sure?
Actually, I don't know about that.
Well, when you have a number, in this case 32 raised to the 7/5 power, which one do you do first, the 7 or the 5?
5.
Doesn't matter. Which one should I do first? 5. What's a fifth root of 32?
2.
2. What's 2 to the 7th? 128. Okay, so that is doable without a calculator. That's the point I wanted to make. We'll stop there. Put 1 in there, we're fine. But you do get some ugly fractions. I would deal with this mess in the parentheses before you multiply anything by pi. Don't start distributing the pi out, just leave it and then put it on the back end. Okay. More importantly, do you understand the setup here? Look at my diagram, see how I did that. Highlighted the area, drew the axis of revolution. If you're feeling saucy, you could draw in that disk, identify r, identify the thickness, make sure you're all in the same variable here, and then set up your integral. And your integral is going to add up all those disks. Okay. Good? Okay, get rid of that. Did all that. Yep. Yep. So in case you care, it's 284.987. Gesundheit. All right, washer method. I'm just going to keep going. We'll see what happens.
Wasn't that answer different than the one we got?
Well, I didn't finish it.
Oh.
I didn't show the antiderivative. The thing that we had up there was the same. Washer method addresses one simple issue. What happens if the rectangle is not touching the axis of revolution?
You get a hole.
Bingo. Also known as a washer. So imagine that disc we had before, if you punch a hole through it, you get a washer. So here's what happens. Now I take that rectangle and I move it up off the axis of revolution. When I spin that puppy around, it generates what's called a washer. It's a little hard to see in the yellow, I apologize. This one gets a little bit more complicated. How do I find, well, that's up there. How do I find the volume of that washer? The volume of that washer is found by taking the volume of the disc and subtracting the volume of the hole. In simplistic terms, we're going to use this. Big R squared minus little r squared quantity times pi. And then times the thickness, which that W will eventually become dx. For our purposes, capital R is going to be defined as the farthest distance away from the axis of revolution. Little r is the closest point to the axis of revolution. Does that make sense?
Yes.
Okay. Are we good so far?
Wait, so big R is farther away.
Yep. Big R is the farthest distance away from the axis of revolution. Little r is the closest distance to the axis of revolution. The rest of the problem is identical to what we just did. If you identify capital R and little r, you find the volume of the washer. Everything else duplicates itself. Come up, take the volume of the washer, take the integral from the limits of, I'm having a brain fart here. Those things on the top and bottom of the integral. Limits of integration. Yeah, I was right. And then plug and chug. Okay. Question?
Yeah. So is the washer like the circle itself or the hole in the middle?
The circle itself. Yeah. The pseudo donut looking thing, which the donut with sharp corners, or just a washer. Donuts or something different. All right. So here's an example. Got that little sliver thing, and how could I get that little sliver thing? I could take a parabola, for instance, and intersect it with a line.
It's like a contact lens.
It looks like a contact lens.
A very pointy contact.
I don't wear contact lenses, so they look like that.
That's a fair point.
Huh?
That's a fair point.
Could just be a lens.
Yeah, big R's the whole.
Times.
From the top, it would be.
I don't know.
Okay.
Here's my axis of revolution. Capital R is the farthest distance away. Little r is the closest distance. And when you spin that bad boy, you end up with this weird looking thing, which is like a cone of shame.
The dog, yeah, the dog.
Except it's got a little bump inside. If you really love your dog, you can have a cone of shame that's got a pillow built in all the way around it. Okay.
Be heavy.
There's another one. How could I get that? Oh, I could take the square root function and some type of parabola, intersect it, spin that thing around. Here's one of those washers we talked about. Here's the whole solid. Okay, so we'll skip that and get right into this fun stuff. Okay, so there's the formula again. This is what we had before. Notice you have to square each individual part. Take the big radius and square it, minus the little radius squared. Because I know where we're going eventually, I'm going to give you a couple things to think about. Number one, am I working with horizontal or vertical rectangles? That's similar to what we did in the last section. Number two, is my representative rectangle touching the axis of revolution over the whole interval? If it's touching, you're going to use a disc. If it's not touching, you're going to use a washer. Notice in both of these situations, your representative rectangle is perpendicular to your axis of revolution. That's important. Okay, did you follow me there? Because eventually we're going to take our representative rectangle and make it parallel to the axis of revolution.
Cool.
No, not so much. Okay, that generates another method called the shell method, but we're not ready for that yet. We're just doing
methods are there?
3. Big radius squared minus little radius squared. Okay. So here's our example that we'll start with. Square root of x. We did this problem the other day. square root of x and x squared. And we get a little rectangle. After looking at the picture, you can see that the big radius is the square root of x. The little radius is x squared. Notice I didn't use top squared minus bottom squared because it'll change if we start changing our axis of revolution. By the way, one nice thing we have going for us is we only spin around horizontal and vertical lines. We don't do anything really weird.
Can you? Do we do the
You
origin?
can, yes.
I like the origin.
What's that?
Show us how to do
Are we ever gonna have to do both?
Let's crawl before we run.
Wait, oh wait.
Hold on, I'm going through it. Okay, so there's my outer radius, there's my inner radius. Again, big radius, small radius. Take each of those and square them. Multiply it by pi. We're integrating from 0 to 1. Why 0 to 1? Because that's the point of intersection between the two functions, which we found when we did this example yesterday. And then dx is the thickness of that rectangle, which should be really small. More so than ever, that differential is really important in the problem. It has to be used to identify that thickness of the rectangle. In the past, when we were just finding the integral of some function which didn't mean anything to us, it's a little bit easier to forget about the dx. Here you can't forget about it because it has a physical property. Okay, let's talk about how to solve that antiderivative. What do you do first? What's the square root of x squared? X. What's x squared squared? X to the fourth. Then what? Keep going, Max. What's the antiderivative of x?
1 half x squared,
Good. And the antiderivative of x to the fourth?
1/4 x,
Nope.
or 1/5 over x, and then x.
1/5 x to the fifth. Plug in 0, plug in 1. Or plug in 1, plug in 0, subtract the 2. Take your final answer, multiply by pi. Okay. 3 pi over 10. Exact answer, or you can take a decimal value. When you're fn inting these problems, you can fn int the whole thing and multiply it out with pi, or you can fn int it without the pi and then multiply it by pi at the end. It's entirely up to you. Molly?
With these problems, do you prefer if they're in that form or decimal form?
It doesn't matter to me as long as you're practicing your antiderivatives. I don't want you to fn int every single problem. There won't be any learning there. Okay. Ready for this? Let's just take a breather for a second.
I thought you said this.
What's that?
I thought you said we aren't doing rotations of.
Oh, no, no, no. What did I say? We're not going to do it around anything other than a horizontal or a vertical line.
Oh, so it's just going to be moved up and down.
Now we're going to start moving the axis, sliding it around.
Oh.
Instead of just being x-axis, we might revolve around the line. Oh, I don't know, y equals 4.
What is this?
Oh.
That's okay.
Like, where would one use this in the real world?
Virtually every field of manufacturing.
Yeah, this one's applicable. Only other
You
things.
took that PW class, right?
But they just do it for you on a computer.
That's true. They
If you draw a good picture, it doesn't have to be 100% accurate, just a good picture, and you do it carefully, and you remember top minus bottom, left minus right, this is not bad. Okay. What's that? No, I didn't. Did I really?
Yeah.
I don't know why I said left minus right is right next. Oh boy. Okay, so let's start with this one. We're going to revolve it around a line other than one of the axes, and in fact we're going to revolve it around the line y equals 3. I'm sure if I click, there's probably a picture associated with this. I don't remember, to be honest, but I'm going to pretend I don't have a picture and start from scratch, because this is the kind of thing you're going to have to do on your homework. And these are functions that are workable here. So what's the graph of x squared plus 2 look like? Ryan? the standard x squared parabola moved up 2. Okay. How about the line 1/2 x plus 1?
Straight line goes through 0, 1. Slope 1/2, so 2 over 1 up.
Oh, 1 and 2, okay. Will it intersect the parabola? I don't think so. It must intersect the parabola, actually. No, it doesn't. Here it is. Okay, 0 and 1. So then our vertical lines are at 0 and our vertical lines are at 1. Okay. We want that region right there. Should have drawn my picture bigger. Because that's the bounded region that we get from all 4 of those things. Okay? And then we want to take that whole mess and revolve it around this line. So there's my line, do the little revolution thing. And then my representative rectangle. Oops, I want that red. We good so far? What's the matter?
Is it still a washer method since at for y equals x squared plus 2 at when x equals 1 the top quarter is touching the line, the axis of revolution?
Yes, because it has to be touching everywhere. So, first things first, find a battery. Okay, first things first. Notice that the representative rectangle is perpendicular to the axis of revolution. All of these problems are going to have that situation. That won't be the case later on, so I still think it's worth going through and noticing that the axis of revolution is perpendicular to the representative rectangle. Is the representative rectangle touching the axis of revolution over the entire interval? No. So therefore, we're going to have a washer. Knowing that we're going to have a washer, I need to identify 2 distances. I need big R and I need little r. That's at 3, by the way. So there's big R. There's little r. Okay, we good so far? What's the matter?
So, for the green lines, and then where x squared plus 2, is that the x equals 1? That should be touching the green line, so like my question is...
It could be, but I don't really care.
So it doesn't matter?
It doesn't matter. No. As long as we have established that it doesn't touch over the entire distance, which isn't going to happen because that's curved, we're fine. You're saying, hold on one second. You're saying that point should be right there.
Yeah.
Yeah. Again, it doesn't matter. Yeah. And that's what causes question was. Since it touches in that one point, would it be a washer or a disc? It does touch in one point, but it's got to touch across the entire interval.
That's kind of my question. How do you know the difference between washer and disc again?
Because it's not touching the axis of revolution over the entire thing. This is going to generate a hole in the washer.
Okay.
Okay. Any others? All right, here we go. What's big R? No.
Y equals 3 minus y equals 1/2 x plus 1.
Not horrible. 3 minus the quantity 1/2 x plus 1. We don't need the y equals.
Oh, okay.
Okay. Why?
Because that's where, like, those are top right bottom.
Bingo. Top minus bottom. Okay, that's where I said top minus bottom and right minus left comes into play here. The top of that radius is the line y equals 3. The bottom is the line 1/2 x minus 1. Plus 1? Plus 1. Yes? No? Good. What's little r?
3 minus x squared plus 2.
Outstanding. Still top minus bottom. Well done. That's the hard part. Now the easy part is remembering the formula and plugging it in. We're going to move the pi out in front. We're going to take the integral from what to what?
0 to 1.
0 to 1 of, what's the formula for this? This is a washer, right?
R dx squared. So
This mess squared
dx.
minus this mess squared, and all of that with a dx stuck on the end of it. Woohoo! Isn't that fun? Here.
Would the same thing like translated like your graphs down so that y equals 3 is the same as y equals 0?
Yes, but then you'd have to change all your functions too.
Yeah, then that just like -3 on the end or something.
So my argument would be, yes, it would work, but the difficulty in changing your functions just to get that to be equal to 0 is more of a pain it's more of a pain than it is to just understand the method for r squared minus. Okay. That's not fun to solve. You have to square that puppy out. So you have actually squaring a binomial inside squaring a binomial. That might be something you want to fn int, but even fn inting it isn't that easy because you got to be careful to type it into your calculator. Okay, but doable. Okay. Still top minus bottom. Now, what's not going to happen for us is we're never going to have our axis of revolution pass through the actual area. Okay, it's not going to revolve onto itself. So if you draw your picture and you have your axis of revolution going through the area, you did something wrong. We're also not going to revolve around anything other than a horizontal or vertical line. So if you get your axis of revolution to be like y equals x, you did something wrong. Livia.
They always tell you what like the revolution, like what the line is.
Yeah. Yeah. And you have to read the problem carefully, so don't assume that it's the x-axis or y-axis. How are we doing so far, kids? Good. Where's the way? Oh, there's the picture. Yep, there's function, top, bottom, yeah, yep. Okay, good, yep. Beautiful, we're done. Do you guys even know what these are? Floppy disks, okay, didn't know. Is it day 106?
No, it's not 103.
103? It wasn't even close.
I was gonna say.
Yikes. Took a stab at it.
Taylor, Max is back down again. You didn't have to look back.
I'm just kind of terrified of the homework.
You should have.
It
was like Max was in point bad.
Yeah, you're right.
Back in.
Shut up.